So this will be the last lecture over chapter 17, so the fifth lecture. So in this lecture, we'll just look at some miscellaneous reactions of aromatic compounds. So start out with phenol. So we've talked about phenol's acidity before, back in the alcohol chapter. So phenol, the hydrogen is fairly acidic, right? It has a pKa of about 10. So why is it so acidic? So if it loses that hydrogen to make the conjugate base, base must be fairly stable for the for phenol to be so acidic. So what stabilizes the conjugate base, if you remember, is you can take that negative on oxygen and you can resonance delocalize it through the benzene ring, so that stabilizes it. Okay, so what if you have other things attached to the phenol, like a methyl group or a nitro group? So if you remember, the methyl group is an activator, so it's electron releasing, it's electron donating group, whereas the nitro group is an electron withdrawing group. It's going to be pulling electron density out of the ring, and that's going to affect the acidity of the phenol. So if we take the proton off of the phenol, so we lose an H+, and then look at the conjugate base. So how is it that the CH3 could, so if you notice here, for the CH3 on the ring, the pKa is less, so it's less acidic. So if it's got an electron donating group on the phenol, it's going to decrease its acidity. Why does it decrease its acidity? So the CH3 is electron donating, so that's going to increase the electron density in the ring, and so that's going to increase the electron-electron repulsion. So that would destabilize the conjugate base. So make it less stable, so less likely to form, so the phenol would be less acidic. If it's a nitro group on the ring, however, so if we look at its conjugate base, so the nitro group must help stabilize it because it's easier to form. That's why the phenol with the nitro group is more acidic, right? It's got a pKa of 7.2. If you remember, as the pKa goes down, the acidity goes up. So how does the nitro group help stabilize this conjugate base, the phenoxide? Well, you can take that lone pair electron, extra lone pair electron on oxygen, and you can delocalize it all the way to the nitro. So we can move the lone pair on oxygen down, move this next double bond over, this double bond over, make a double bond to nitrogen, and those electrons on the oxygen. So we can delocalize the negative all the way onto the nitro. And if you remember, anytime you can delocalize charge, that stabilizes it. So this conjugate base is more stable, which means the acid is more acidic. It's more likely to lose its proton. So just in general, then electron donating groups will increase the acidity or decrease the acidity of phenols, and the electron withdrawing groups will increase the acidity of phenols. So this would be kind of an extreme example. So if you have the phenol with 1, 2, 3 nitro groups on it, that's what's known as picric acid. So it's got a pKa of 0.4, so that's quite acidic. This is a lab hazard, so let's not be making any picric acid in lab because it explodes at greater than 300 degrees Celsius. It'll even explode by sound. Percussion can make it explode, or if it's heated too fast, it can explode. Okay, so phenols, so that's a very strongly activating group. The same would be if it was a nitrogen there, NH2, very strongly activating. And if it's such a strong activator, then they can undergo electrophilic aromatic substitution without a catalyst. So if you add a Br2, you don't even need the Br3, but then you can add a bromine to phenol, and you could potentially add 2 bromines, or you could even add 3 bromines because the phenol OH is such a strong activating group. So that would be one problem in these electrophilic aromatic substitutions, is sometimes it can be difficult to stop at one reaction. If you have activating groups on there, they could potentially do a second or a third reaction. Okay, so phenols have a lot of importance in biological chemistry. We've talked about this back in the alcohol. Phenol is part of the tyrosine amino acid, for example. So this type of oxidation has lots of biological implications. So you can oxidize phenols. So if you oxidize it with CrO3 and H2SO4, basically what happens is you form this chromate ester, and then a water molecule attacks. So take a lone pair on water, make a bond here. Those electrons go there, those go there to make a C double bond O, and then chromium accepts those electrons, so chromium is reduced. And then if we lose a proton from here from water, and now we have this, which then this can form another chromate ester. And once you have that chromate ester, then it can be oxidized. So you can make another carbon oxygen double bond, and then you make what's known as a quinone. So quinones can be reduced to give what are known as hydroquinones. So if we take a quinone and react it with an electron, so let's just follow our electrons here. So if we give one electron there and give this electron to oxygen and the other electron here, then you would have this, right? And then another electron, so a 2-electron reduction. Okay, so let's see. So let's take this electron and bring one of these over to make a double bond there, and bring this over and one of these to make a double bond there, and this up here, and then this there, then that would give you this, right? And then if that picks up 2 protons, then you have what's known as a hydroquinone. So this is important biologically. Quinones and hydroquinones. Hydroquinones are part of the electron transport chain. So they're what helps shuffles electrons between molecules in the electron transport chain. So this molecule is what's called coenzyme Q, or sometimes called ubiquinone. So if it picks up 2 electrons and 2 protons going this way, so if the quinone is reduced, then something is oxidized. So what's oxidized is NADH, and then that will give you the hydroquinone in the reduced form. Or it can go backwards. It can give up electrons and protons and become oxidized. And if something is become oxidized. So if it's oxidized, then something is reduced, which would be NAD plus in this case. So the important is quinones or phenols are very important biologically. So biochemistry, biological chemistry is just basically basic organic chemistry, just much more complex molecules. Okay, so benzene can be reduced. So we've seen if you take cyclohexene, you can just take H2 and palladium, and you can add hydrogen and hydrogen across the double bond. You can do that at room temperature. You can do that at atmospheric pressure. So basically all you'd have to do is just put a hydrogen balloon on top of your reaction, and the reaction works at room pressure, room temperature. But that's not the case for benzene, right? Because because benzene is aromatic. And if you get rid of those double bonds, it's no longer aromatic, and aromaticity is very stabilizing. So if you want to reduce benzene, you have to beat on it. So you have to go to higher temperatures typically and much higher pressures, so 30 atmosphere pressure, and then you can reduce the double bonds in benzene to make cyclohexane. So some other ways to reduce it, you can do what's called a Birch reduction. So if you take benzene, so this will be elemental sodium, so it has 1 valence electron, and then if you do that reaction in ammonia and methanol, then you can make the 1,4 cyclohexadiene. So what's kind of unique about that reaction is if you make dienes, they like to be conjugated, right? But these dienes are isolated. So it's one way to make isolated double bonds. So the basic mechanism, So let's just follow the electrons. So let's split this pi bond. So put one electron on this top carbon and move one electron here and one electron over to make the double bond, and then the other electron here, and then let's take that electron and put it on that carbon, and that will give you this, right? And then carbon with the lone pair is very, very basic, so it pulls off a hydrogen from the solvent to give you this. And then if you have a second equivalent of a sodium, so you need two equivalents to do this reaction. So another sodium gives up its electron. Now you have this carbanion, and then it pulls off a hydrogen from another molecule of methanol. And then you've got the 1,4-cyclohexadiene, so you've reduced the double bonds. And so now those two double bonds would just undergo normal alkene reactions from chapter 8. Okay, so the reaction can be a little bit tricky depending on what's on benzene, because if benzene is substituted, then there's two different products that you could form. So if that's an electron donating group, so you end up with the diene such that the electron donating group is on the double bond and not here where it's between the double bonds. But if that's an electron withdrawing group, then it's the opposite. So electron withdrawing groups ends up between the two double bonds and not on the double bond. So that's an example. Right, this would be an activator. So that's a electron donating group. So if you did the Birch reduction here, right, that would be your major product where the OCH3 is on the double bond. And this would be a meta director, so deactivator. So that would give you the product with the cyclohexadiene where the group is between the double bonds. Okay, so just a little bit more about the benzoic position. So we've talked a lot about the reactivity of the benzoic position between organic 1 and organic 2. So we've looked at this before. If you take that and react it with NBS and CCl4, or it could be Br2 and light, or right, Br2 and heat, you can do free radical bromination at the benzoic position, right? And why the benzoic position? So these are free radical mechanisms. That's a good place to put a radical, right? Why is that a good place to put a radical? Because it's resonance delocalized. So that's where the radical is going to form, so that's where the bromine is going to end up at. So that would be your major organic product. Or if we did this reaction, to just show you how the benzoic position can influence reactivity. So an alkene with HBr. First of all, you want to recognize these double bonds and benzene are not going to react, right? Because you don't want to lose their aromaticity there. So this is the double bond that's going to react. And if you remember from chapter 8, alkene with HBr does Markovnikov addition of H and Br. But Markovnikov's rule doesn't help you in this example, right? Because this carbon has one hydrogen and that carbon has one hydrogen. So where does the hydrogen go? Markovnikov's rule does not help you, but the stability of the carbocation intermediate does, right? Because if you add the hydrogen to this carbon, then you get, so if the H goes there, then you get this carbocation, which is secondary and benzoic. And then the Br minus can attack there, right? If you added the hydrogen to this carbon, then that would lead to this carbocation, which is just secondary, and that's worse, right? So that's not what's going to happen. So even though Markovnikov's rule does not help you, because you don't, right? Because if you remember, Markovnikov's rule says put the hydrogen on the carbon that's got the most number of hydrogens, but these both have one, so that doesn't help you. But if you look at think about how the reaction occurs, and that it's a carbocation intermediate, and you want to make the most stable carbocation, then of course you want to put the hydrogen on that carbon so that you make it secondary and benzoic, and then that's going to lead to this as the major product, and none of that as the major product, or none of that as a product, or if you get any of that, it's going to be very minor amount. So this benzoic position can help drive product in the E2 reaction, right? So if you did this reaction, so if you remember from organic 1, that's a recipe for an E2, because that's a strong base. That's a secondary alkyl halide with heat. That's a recipe for an E2, which means you're going to either take a hydrogen from here or you're going to take a hydrogen from here. So you could either make this alkene or that alkene. So you don't make this one. Why not? Because this double bond is isolated. This double bond is conjugated. And of course it's conjugated with benzene. And of course conjugated double bonds are more stable. So when this reaction happens, that hydroxide will take that hydrogen, those electrons go there, and that bromine leaves, and you make a disubstituted alkene. Of course both of these are disubstituted, right? But only one of them is conjugated, and you want to make the conjugated one. Okay, so what about oxidation? So if you have alkyl groups on benzene, then they are susceptible to oxidation. So we won't look at the mechanism, just have to know how to predict the product. So basically what happens is the benzoic position gets oxidized. So it's oxidized if it has H on it. And this one's benzoic. But there's no hydrogen there, so that one doesn't oxidize, but the one on the right does. So basically you cleave that double bond and that carbon oxidizes to a carboxylic acid. So you make benzoic acid derivative. So same thing here, those are benzoic positions and they have hydrogens. So they're going to oxidize, so you're going to cleave it there and you're going to cleave it there. And that would be your major organic product. So again, all benzoic carbons that have hydrogens will oxidize to benzoic acids, to carboxylic acids. Okay, lastly, just to contrast how an ether would react if it's aromatic ether versus not. So we talked about this back in the ether chapter. So if you remember an ether with HBr, we'll pick up a hydrogen, and then Br minus can attack, kick that off. And now you have a alcohol which could react again. All right, so then water leaves to make that carbocation, and then Br minus adds there, right? But if it's aromatic ether, it's different. So that's not what's gonna, part of that's gonna happen, but not all of this. So you would protonate there. And then Br minus would attack here and kick this off. And now you're done, right? That's your product. So what's different is that's an aromatic alcohol, and you're not going to protonate that alcohol, and it's not going to leave because you don't want to make that, right? That's very unstable. So once you make that phenol, it's done, and it would only kind of do half of this reaction. Okay, we'll stop there.